Alright, for this first problem here, we're going to start by drawing the free body diagram for this object here, suspended from two strings. So we, of course, have the force of gravity going straight down. We have Ft2 going up and to the right, and we're going to have Ft1 going up and to the left. For this next question, we want to know what happens when we change that string on the left. So it's attached to as a right angle. The first thing I would think about is just redrawing the forces we have. So when we transition to that new situation, we're still going to have the force of gravity going down, of course. We still have Ft2 going up at an angle, but now Ft1 is going to go directly to the left. And what we want to think about here is whether this Ft2 is now greater than, less than, or equal to the initial value. We're going to justify it qualitatively without using equations or calculations. So where I would really start with this is focusing on the y components. Okay, that's what I would think about first. So in this first diagram, we have x and y components for both upward forces, okay? And ultimately that means that these two y components are going to balance out the force of gravity here. However, when we tie that second rope, so this is just horizontal, it means there's no longer a y component to that rope. It's only rope 2 that has the y component. And so that means now that the y component from the tension in rope 2 must balance the force of gravity, whereas before the y component of 1 and the y component of 2 together balanced it. So because 2's y component must balance it on its own, and the angle, as you'll notice, has not changed, okay, it's still theta 2, all right, that means that Ft2 must exert a greater force because now it's balancing all of gravity on its own. For the second part, we want to determine the vertical component of F2 without doing calculations, and really it's basically what we said here. We know that this force and this force must balance each other, so that vertical component is equal to the force of gravity, because it's the only other vertical force. Alright, for this next one, we're going to start once again by drawing our free body diagram. I'm just going to move the block down here so I have a little more space, but we're going to start with the force of gravity, of course. We know that's there. It's on a surface, so we have our normal force. We're going to have that F1 going up at an angle here of theta above the horizontal, and because it's pulled across a rough horizontal surface, that means we're also going to have the force of friction here. For B, we want to derive an expression for the normal force. That's a y thing, so I'm going to set up my may in that situation. Okay, and before I do that, actually, I want to go ahead and componentize that F1. So that vertical component is going to be F1 sine of theta. The horizontal is going to be F1 cosine of theta. And so what that y equation looks like is F1 sine of theta plus Fn minus Fg equals 0. Right, we're going to rearrange that to solve for Fn, and we're also going to sub in for Fg, just make that be mg. So I'm going to say that Fn is going to be equal to mg, okay, subbing in for gravity and moving it over to the other side, minus F1 sine of theta, and that is in terms of the variables that I am given there, m, F1, theta, and fundamental constants. For C here, we want to now derive an expression for the coefficient of friction. That's going to be an x thing. I'm dealing with that force of friction, so I'm going to set up my max here. All right, I'm told that since it's moving at a constant speed, I know that that acceleration is 0, and so that equation ends up becoming F1 cosine of theta minus F equals 0. All right, I'm going to move that FF over to the other side, and I'm going to make that substitution. The FF is mu times my normal force here. All right, I just found an expression for my normal force, so I can substitute that in. So I have F1 cosine of theta equals mu times mg minus F1 sine of theta, and so mu, it's a little bit of a messy expression here, but mu becomes F1 cosine of theta divided by mg minus F1 sine of theta. Unfortunately, there's no simplification we can do there. That's just going to be our equation. All right, for this next problem here, this is an experimental design one of sorts. We want to go ahead and determine the coefficient of static friction between a wooden block and the horizontal surface of a desk. So we're going to go ahead and design a procedure to do that. But what I would do before we do that is really think about the forces that are going to be present in this situation. And also think about just some of the basic ideas related to static friction. So let's think about this situation. We have a block sitting on a desk. We know there's going to be the force of gravity acting on the block, the normal force, of course, all right? And if we're thinking about static friction, right, we're going to have to apply some horizontal force to it to create static friction. Otherwise, if it's just sitting there, there is no force of static friction. So I'm going to have a pulling force going to the right, all right? And I'm going to make it horizontal because then we don't have to worry about an angle. And that's going to be balanced out by that force of friction going to the left. Now, the other thing to think about here with force of friction is that force of friction is less than or equal to mu s times our normal force. So what I'm going to do is I'm going to think about that situation where we are breaking static friction, okay, that point where the object begins to slide, all right? And so I'm going to design my experiment so that we are breaking static friction, and that means that the force of friction in that situation will be equal to mu s times our normal force. So we want to keep that in mind as we're doing that experiment, that we are at that point where we've maxed out the force of static friction. Now that I've thought about that setup, let's think about what we're actually going to need to do. So like I said, we are going to need to be in that situation where friction's at a maximum. Things we're going to need to measure. We're going to need to measure our pulling force, because if we think about our horizontal forces, okay, we know that in that situation, right where it begins to move, we have zero acceleration, and our pulling force is equal to the force of friction. So that's one thing we're going to need to do. We also need to get our normal force. Right, that allows us to find force of friction. We also need to get our normal force, and that's just going to come from the y stuff, and the normal is going to be equal to the force of gravity, and we can get that by measuring the mass and multiplying by 9.8. So we're going to need to get mass in order to ultimately find normal force, and we're going to need to get the force of friction, all right, or the pulling force in order to find the force of friction. So I'm going to start by just saying place the block on scale to get the mass of the block. Next thing I would do is I would attach a spring scale to the block. That's probably the easiest way to measure force, although you could also measure it with the force probe. Okay, either one would be a valid way of measuring force. But attach a spring scale to the block, all right, and slowly increase that horizontal force on the block until the block begins to move. All right, and that really is the key here. We want that point where the block begins to move. All right, that's the point where we've broken static friction. And what we're going to do is we're going to record the maximum force that we applied to the block. If we were doing this with a force probe, we could get a nice graph and just find that maximum. So that might actually be an advantageous way of doing it, but I think you could do it with a spring scale as well. But the key is we're increasing the force that we're pulling with until it begins to move and recording that maximum force. Last thing I would say here, and I realize that the problem didn't specifically ask for how we would reduce uncertainty, but I would add mass to the top of the block to vary the normal force. And ultimately why I'm doing that is I'm going to think about using a graph to find this force of friction in the end. I guess you don't necessarily have to do this here because there's nothing that says you have to create a graph here, but I think the best way of doing this, if you can create a graph to solve a problem, I think you always should. All right, it reduces a lot of uncertainty and makes for better results. So I'm going to add mass to vary the normal force. That will also vary the force of friction then, and then we can use a graph to ultimately find that coefficient of friction. All right, for B, this analysis part, we know that the force of friction is equal to the pulling force, as we mentioned before, since the acceleration is 0, and the normal force is equal to the force of gravity, so m times g. Okay, so we can go ahead and calculate the normal force and the force of friction for each trial. And then what we want to do is, if we're thinking about this equation, okay, we varied the force of the normal force, all right, and measured the force of friction each time. Okay, that's essentially what we did. So what I'm going to do is I'm going to think about how we could potentially graph this to lead to a linear function and use that slope to get the coefficient of friction. So the best way of doing this, and this matches with our x is the independent variable, y is the dependent variable, is we already have this equation here, Ff is equal to mu times our normal force, and that's already set up so that we have it solved for the independent variable, which is Ff in this case. So if we compare that to our equation for a line, y equals mx plus b, if we put Fn, our independent variable on the x-axis, Ff, our dependent variable on the y-axis, our slope will set up to be the coefficient of friction, which is quite convenient. So we're just going to create a graph here that is Ff versus Fn, and then the slope will be equal to mu. And that's how we can ultimately find the slope in a way that really reduces the error. For this last part here, we want to know how we could change this so that we're now solving for the coefficient of kinetic friction rather than the coefficient of static friction. And really the key is with kinetic we're moving, sliding, instead of static when we were stationary. So the first thing we're going to need to do is we're going to need to actually get the object moving, okay? Get to a point where it's sliding rather than just bringing it to that point where it begins to slide. And the other thing I would do here, and this is really just to maintain this basic relationship where Fp equals our force of friction, is say that we'll slide it at a constant speed, okay? So that's the other thing I would do is just slide it at a constant speed here, and then we don't have to worry about measuring the acceleration.